So in this video, we're going to do two problems dealing with exponential growth and exponential decay. When we're looking at growth and decay, for growth, we're looking at the general equation y equals a times 1 plus r to the t power. That rate is going to be the rate of growth. T is going to represent the time since whenever they specified was the start time, and A is your initial amount. So in this problem, it says in 2006 there were 1,020,000,000 people worldwide using the internet. At that time, the number of users was growing by 19.5% annually. So we've now identified our initial amount as the 1,020,000,000 people, and we also have our rate of growth, which is 19.5%. So when we plug this into our equation, we're going to get 1,020,000,000, and then our rate is 1 plus 0.195. You have to remember to change that to a decimal, and we want that to go away. T. Now in this problem, T is representing the number of years since 2006. So once we get this equation, we have that our base is 1.195. So we're going to take 1,020,000,000 times 1.195. And in this case, in 2016, it's been 10 years since the start date that they were talking about. So you can simply go to your calculator and you're going to put in 1.195 to the 10th power, and do that first and go ahead and push enter. And then you're going to do times 1,020,000,000, and you get, wow, that's a big number, 6,057,301,968. And I would say that I could transfer that easily to that other page, but I can't. So know that that would be your answer in 2016, how many internet users there would be. 6,057,301,968 users. So going back, I'll let you guys write that down there. I don't remember the number from the calculator. So now let's do one that involves exponential decay. And in our notes, that was back here. So when we're talking about decay, the pressure of the atmosphere is 14.7 pounds per square inch at the Earth's surface. It decreases by about 20% for each mile of altitude up to about 50 miles. So you're looking for words like increases and decreases to know if it's going to be exponential growth or exponential decay. So we're starting off with the same formula that we had last time. That T should be in the exponent spot. And so we're saying our initial amount in this is 14.7 pounds per inch square, so that's A. This is our rate. So we have 14.7 times 1 minus 0.2 to the T. So if I simplify this, because this is a little easier to do than the last one, we have that our base in this case is 0.8, and so it's between 0 and 1, which is what makes it decay. Now it says draw a graph to represent the atmospheric pressure for an altitude from 0 to 20 miles. Well, to do that graph, you would start plugging in where T is 0. What would you get? Well, you get 14.7 because that's your initial amount. You could sketch the graph. You don't have to do every single point from 0 to 20 because that would be a little bit insane, but I'll just do 10 and 20. So when I plug in 0.8 to the 10th power, and then I believe our initial rate was 14.7. we get 1.58. Which makes sense because we have a decaying function here. And then when we plug in 20, it's going to be even smaller than that. So we're going to do 0.8 to the 20th power times 14.7. Oops. Times 14.7. And we get 0.17. So in doing this graph, I'm not sure why I'm going to erase that. We just need the first quadrant. To make our numbers go a little more I mean. So we have 0, 14.7, 10, 1.58, and then it's going to keep getting smaller from there. Pretend that looks like a good curve. So it would look like that. So that's what exponential growth and decay functions are going to look like. And that's it.